Welcome to IB Chemistry exam preparation, exam tips for both standard level and higher level. Today through our lesson, we're going to practice on past paper questions taken from paper 1 for topic 11.1, Uncertainties and Errors in Measurements and Results. We're going to answer multiple choice questions related to this paper. So let's get started. Now we're going to start with the first question. So inside this question, which could be the best method to decrease the random uncertainty of a measurement in an acid and base titration? Here the question is asking me about reducing a type of error, which is the random error. Here you need to refer back to our lesson about measurement and uncertainty. You can go back to the types of error. We discussed previously that any time we want to reduce random error, we need to go through the repetition. So we need to repeat the experiment for several times. This is so important before starting reading the possible answers. So A, ensure your eye is at same height as the meniscus when reading the Buret. Of course, no. This will reduce a type of error which is considered as being parallax error. Use a different indicator for the titration. This is more as being a method error, so it is a systematic error. Use a different Buret, or repeat the titration. The answer is definitely D. Anytime you want to reduce random error, remember that you have two different ways to reduce. You can either repeat or you can use more precise equipment. In this question, it is the repetition part. We're going now to start with question number 2. Using an accurate pH meter, the pH of the lemon was found to be 2.3. Some students deduce the pH of the lemonade after titration with 0.1 mole per decimeter cube sodium hydroxide solution. Their determined values of pH were 2.4, 2.5, 2.4, and 2.4. What is the best description of the precision and accuracy of these measurements? In order to describe how accurate is the data, so we need to go through the average calculation for the pH values for the 4 trials, and we're going to compare it with the actual, which is the literature. So this is my actual. So the first step is to find out the average. When I'm going to take the average, I'm going to take the values which are 2.4 plus 2.5 plus 2.4 and another 2.4. Then I'm going to divide over the total, which is considered as being 4, and your final answer, it is 2.425, which is approximately 2.43 after rounding. So if we want now to compare the experimental average results with the actual that we have obtained or given inside the question, we're going to find that our measurement data is described as being accurate since it is so close to the actual. So for the accuracy, we're going through accurate as a final answer. So the final answer is either C or D. Continuing with the precision part. Here we need to refer to the actual value. If we look at the actual value, we're going to find that you have 2 decimal places presented inside the final answer. 2 decimal places. And the decimal places, it's so important for the precision of the equipment that should be used inside the lab. So the inexact number here, it is actually the 0. So I have 2.30. The inexact number, it's my 0. If I look at the values given from the pH meter, which was used inside the lab, I'm going to find that I have only one decimal place given. So the inexact number is in the first decimal place. In this situation, I cannot describe at all that my values are precise, since this is an indication that the equipment or the pH meter that was used, it was not so sensitive. It should give me 2 decimal places, and the only difference between one and another should be in the second decimal place, not the first. So in this situation, I'm not going to describe my data as being precise. They are actually not precise, and your final answer, it's a D answer. Continuing now with question number 3. In question number 3, we have a student measured the mass and volume of a piece of silver and recorded the following values. Which value in gram per cubic centimeter for the density of silver should the student report in her laboratory? Let's look at what do we have data. We have the mass of an empty weighing bottle. We have the mass of the weighing bottle with a piece of silver. And we have the volume. So let's start with the rule. The question is asking me about the density as a final answer. So what is my density as a rule? So the density will be the mass of the piece of silver divided over the volume. How can we find the mass of the piece of silver? We're going to subtract the mass of the weighing bottle with a piece of silver, which is 11.5700 minus 1.0800 for the empty weighing bottle. After that, we're going to subtract our final, or we're going after subtraction to divide our answer by the volume of silver, which is considered as being 1.00. Of course, inside paper 1, you are not allowed to use calculator. So you may think about this question without even doing the calculations. So here I need to refer for a study tip. If you remember, whenever you want to divide, you need to have your final answer into a correct number of significant figures. So let's look at the significant figures given in each value inside my density rule. How many significant figures do we have inside this number? You will count. The zeros are counted here. So I have 4, 5, and 6 significant figures. For the mass of the empty weighing bottle, I have 4 and 1, so it's a 5. For the volume, I have a 3. So definitely my final answer should be 3 significant figures as a final answer. Since according to the law, whenever we want to divide, our final answer should be correct into the smallest number of significant figures. And this was discussed inside our lesson, which we took it previously when talking about the significant figures number. So from here, I can start looking at my choices. I need to think about the final answer into which I have 3 significant figures. So in A, I have 4 significant figures, so this is incorrect answer. In B, I have 4 and 5 and 6, so this is also incorrect. And finally, going through the C, we're going to find that we have 3 significant figures, so this is your final answer. So the answer, it's a C actually. Now continuing with more ideas. Question number 4. A student carries out a titration 3 times and obtains the following volumes. 3 plus minus 0.1 cubic centimeter, 3.2, 3.2, and each is 0.1 cubic centimeter. What is the average volume? Another time when we want to take the average, we're going to take the 3 trials value. So it's a 3 plus 3.2 plus 3.2, and then you're going to divide over 3. And your average value, it is 3.1. So the final answer is actually 3.1. Why do we have 1 decimal place here? Since according to the rule, whenever we want to add or to subtract, our final answer should be only 1 decimal place. So this will help me if I look at the choices given and I don't want to apply on calculations without a calculator definitely. The B, it will be incorrect, and the D, it will be also incorrect. So my choices should be 3.1 and 3.1 for A and C, even if I didn't apply on calculations. Now I need to write down the absolute uncertainty for my average. How can I find the absolute uncertainty? It is so easy if you are talking about average. For the absolute uncertainty, you're going to take the 0.1, which is the absolute uncertainty of your first value, plus the 0.1, which is the absolute for the second, plus 0.1 for the third, and you're going also to take the average. So it would be 0.3 divided over 3, and your final answer, it is 0.1 plus minus. So the average absolute uncertainty is as the same doing the calculation using the average volume. So your final answer is 3.1 plus minus 0.1, and it will be definitely the A answer. Now continuing with 5. In an experiment to determine a specific quantity, a student calculated that her experimental uncertainty was 0.9. So this value is the percentage uncertainty, and her experimental error was 3.5. So the experimental error obtained is 3.5. Which statement is correct? Before starting reading A, B, C, D choices, here we need to make a small comparison between both values. We're going to find that 0.9 percentage is smaller than 3.5 percentage. And remember that the first percentage, it is taken from the uncertainty, which is of course taken from the random errors. But the second, it is for the percentage error as experimental percentage error. Here we have a very important rule. Whenever the percentage error is higher than the percentage uncertainty, in this situation our experimental data or experimental method contains both systematic and random, and this is so important to be remembered. Now I will start answering. Only random uncertainties are present inside this experiment. Definitely this is incorrect. If I have only random, so the percentage uncertainty should be larger than the percentage error. Both random uncertainty and systematic error are present in this experiment. Yes, this is actually a correct answer. So if the percentage uncertainty was smaller and your percentage error was higher, this is an indication of having both systematic and random at the same time inside your experiment. Number 6. A student weighs a standard 70-gram mass 5 times using the same balance. Each time she obtains a reading of 71.2. So for the 5 trials, each time she obtained the same value. This is an indication that the data values are precise. This is a very important thing that we should keep inside our mind. Which statement is correct about the precision and accuracy of the measurement? If you look at the actual value and you compare it with the experimental trials, you're going to find that the value is so far. In order to have it as accurate as possible, it should be very close to the actual. So according to my experiment, the data is actually based on what is given. It is precise. So the values are each time the same. So they are precise. But according to the accuracy, it is inaccurate. It is far away from your actual. So this is a B answer. Precise, but it is inaccurate. Question 7. A student performs an acid-base titration using a pH meter, but forget to calibrate it. Miscalibration or incorrect calibration. So this is a defect in the instrument. You need to remember that this is an indication of having a systematic error. Which type of error will occur and how it will affect the quality of the measurement? So definitely if you have a miscalibration of any device inside the lab, you are talking about systematic error. And systematic always affects the accuracy of your results. So the answer, it's a B answer. Anytime you have systematic, it affects the accuracy, but the random error affects the precision part. Continuing now with question number 8. How are the uncertainties of two quantities combined when the quantities are multiplied together? This is a rule. If we want to go through calculations related to multiplication, so what we're going to do for the values, definitely we're going to take the percentages, and we need to remember that the percentages should be added together. This is one of the rules. We're going to apply on the calculations of the percentage uncertainty after being added if you have a multiplication or division later, when we're going to apply on paper 2 questions in the second video. Question number 9. The rate of a reaction is studied at different temperature. Which is the best way to plot the data? Here we're going to refer to the graph, so I need to revise something now. As you know, we have x and y. The y, it's always for the dependent variable, which is the variable that we are measuring. But on the x, I have the independent variable. So it's what I am changing. So based on these two basic information, now I'm going to look on my question. The rate of reaction is studied at different temperatures. So what's the variable that I am changing here? I'm actually changing the temperature. And each time I'm changing the temperature, I'm focusing on the rate. So the dependent here is the rate, and the independent is the temperature, which is the variable being changed during the chemical reaction or during your experiment. So based on that, the answer it is, on the x-axis, we will have the temperature, which is considered our independent variable. Continuing with question number 10. What are the absolute and percentage uncertainties for the change in mass? The question is asking about the change in mass. Whenever we want to calculate the change in mass, definitely we're going to subtract the final mass from the initial. So it is 42.35 minus 22.35. The numbers given are so easy. So even if you don't have the calculator, you're going now to subtract 42.35 from 22.35 and your final answer is definitely 20. If I want to take into consideration the number of decimal places, so it should be 2 decimal since I'm doing a subtract. Now going back to the question, I'm not actually done. The question is asking me to find out the absolute and the percentage. Whenever you are subtracting or adding, what we're going to do for these both uncertainties, according to the rule, we're going to add them. So 0.05 plus 0.05, it will be plus minus 0.1 percentage or 0.1 as an absolute uncertainty in a gram. So if you've got two absolute uncertainties and you add or you subtract, what you're going to do for these two absolute uncertainty, you need to add them. Adding them down, so my final answer, it is either B or the D. The question is continuing with the percentage uncertainty. What's the rule to obtain the percentage? You're going to take your absolute, which is 0.1. You're going to divide over the value, which is the delta mass, 20, and it is multiplied by 100%. So if you want to go through the answers, of course it's not possible to be a 0.1. Even if you don't want to do a calculations, if you don't want to do a long division, there is a sense of common here. Think about which one is the incorrect answer. Definitely your final answer, it's a B answer. And if you want to check, you can do the long division. So in this situation, you will divide 0.1 and you're going to divide it over 20. You will firstly overcome the point, so you will multiply by 10 and you will multiply by 10. So it will become a 1 divided over 200. You can apply then the long division and it will be a 0.005. Then this number, it will be multiplied by 100 and your final answer, it will be the half. But there is no need to go through all these steps as a paper 1 calculations. Now we're going through question number 11. Buret reading for a titration are shown. You have final Buret reading and you have initial Buret reading, trial 1, trial 2 and trial 3. What is the mean titer and what is the absolute uncertainty of the mean? When talking about the mean, so I need to calculate the average. Average of what? It is the average of the liquid which is used in each trial. So if I have final Buret and I have initial Buret, I need to subtract the initial from the final each time in order to find the total volume that has been used inside my titration. So 11.35 minus 0.2, it is 11.15. 13.5 minus 24.6, it is 11.1. And finally here, it is 11.2. Now after having the values, we're going to add them together in order to determine the mean, and we're going to divide over 3. So this is for the mean value, which is the same as the average. If you're going to take the average of these 3 numbers, you're going to find that the final answer, it is 11.15 cubic centimeter. Now the point is how to find out the absolute uncertainty, which is the plus minus uncertainty presented here. Since we do the average and we have firstly a subtract, so we need to remember that we firstly subtract And when you subtract, you have two values, and each one is plus minus 0.05. So for each value given after subtracting, the volume of titrant used, it will be plus minus 0.1. Since we're going to add both uncertainties. So plus minus 0.1 for each one. So if we want to calculate the average, another time we're going to take 0.1 plus 0.1 plus 0.1, and we're going to divide over 3. Definitely the final answer, it will be plus minus 0.1. Let's go through the possible answers given. If you look at the answers given, you're going to find that in the first one, it is 11.1. If you look at my final answer as a mean, the 5 can give the 1, so definitely it's not a 1 at the end, so this is incorrect answer. Continuing with B, the average is given in a correct answer, but the problem is in the plus minus uncertainty, so another time this is incorrect. For the C, it is 11.2, which is the rounding part of the 11.15, but the problem is in the absolute. So the best answer, it is 11.2 plus minus 0.1, which is a D answer. Continuing with question number 12. How should the difference between 27 plus minus 0.3 and 9 plus minus 0.2 be shown? The difference, so I need to subtract 27 minus 9.0. This is a 27.0. I'm going to put it and take the 0 into consideration for the correct number of decimal places. If you don't want to subtract, there is no need, since all numbers which are given inside the choices, they are 18.0, so I'm sure that this is 18.0. After that, I will look for the plus minus. This situation, I took the 0.3 and 0.2, and I need to add them together. Since the absolute uncertainty, whenever we use addition or subtract, we need to add them. So it is plus minus 0.5. So my final answer, it is a C answer. Continuing with question number 13. The molar mass of a gas determined experimentally is 32 gram per mole. Its literature, it's the actual value, is 40 gram per mole. What's the percentage error? Now we need to remember the rule of the percentage error. In the percentage error, we take the absolute uncertainty, since it is a positive answer, the actual value, which is 40, minus the experimental value, which is 32, divided over the actual, which is 40, times 100%. 40 minus 32, it's an 8, divided over 40, times 100%. Going through the long division part, so 8 divided over 40. You cannot divide, so you're going to add a 0 and you're going to add a decimal. 40 times 2, it's an 80. And your final answer, it's a 0, 0. After subtract. So here, it will be a 0.2 as a final answer, multiplied by 100. And your final answer is 20%. So you're going to circle the 20%. We're going now to continue with the last question, which is the question number 14 for our practice for today. Rose carried out an experiment in which she measured a temperature change. Her data are shown in the table. we have the initial temperature and the maximum temperature. The temperature change should be quoted as. So I want to calculate delta temperature. I'm going to subtract 37.6 minus 18.7, and your final answer is 18.9. I'm going to leave it as 18.9 since I have one decimal place here and one decimal place here, so my final answer should be one decimal place. Now another time, what I'm going to do for the absolute uncertainty, if I am dealing with addition or subtract, I need to add them together. So 0.5 plus 0.5, and your final answer is 1.0. So this will be a 1.0 degree. Based on the options given, your final answer, it's the C answer. These are some of the past paper questions taken from paper 1 for chapter 11.1 for the measurement and uncertainty. I'm going to apply on more ideas and more questions for paper number 2. So thank you for watching, and I hope to see you later in the second practice, which is based on paper 2 questions.